After demolishing 28 facts about the solar system, you thought you'd hit rock bottom? Oh, naive Earthlings. The universe still has an entire arsenal of false truths, and now we'll reveal 7 more. Buckle up. The debunking begins. In space, water boils. Or does it freeze? Here's a dilemma that has forever divided space enthusiasts. Water exposed to cosmic vacuum boils instantly, some claim. No, it freezes immediately into blocks of ice, others counter. It's the phase transition derby, the thermodynamic battle of the century. And like any good scientific dispute, both sides are right and wrong at the same time. The truth is so bizarre, it seems straight out of a psychedelic sci-fi movie. Water in space does both things simultaneously. Here's what actually happens. In the vacuum of space, without atmospheric pressure keeping them in line, water molecules immediately start boiling. Doesn't matter that the temperature is below zero. Without pressure, the boiling point crashes. At sea level, water boils at 212 degrees Fahrenheit or 100 degrees Celsius. On top of Everest, it does so at 158 degrees Fahrenheit or 70 degrees Celsius. But just outside the atmosphere, it boils even at minus 58 degrees Fahrenheit or minus 50 degrees Celsius. And while the water boils furiously, something magical and terrifying happens. Evaporation carries away so much heat, latent heat of evaporation for the thermodynamics nerds, that the remaining liquid cools drastically. In milliseconds, the temperature plummets below freezing, and boom, you have water simultaneously boiling and freezing. Astronauts who've witnessed water leaks in space describe a surreal spectacle. Water exits, starts violently boiling, forming bubbles that expand in the vacuum. But while boiling, it transforms into a cloud of sparkling ice crystals that slowly sublimate, going straight from ice to vapor. It's like watching snow form from nothing and disappear as you watch. Canadian astronaut Chris Hadfield described the experience of seeing urine expelled from the ISS. Yes, they dump it out. It comes out as a liquid, immediately boils, freezes into ice crystals that sparkle in sunlight, then sublimates into a vapor cloud that disperses. It's disgusting and beautiful at the same time. They call it the urine constellation. You won't find it on star charts. The Sun sits still at the center of the solar system. Ah, the dear old model of the solar system, with the Sun sitting still at the center and planets orbiting around like bees around a flower. So simple, so elegant, so completely wrong. The Sun doesn't sit still at all. It dances, wobbles, and staggers like a drunk giant at a cosmic party. The secret lies in the barycenter, the solar system's center of mass. When two objects orbit each other, both rotate around their common center of mass, which coincides with the larger object's center only if its mass is enormously greater than the smaller object's. With a small planet like Earth, which is 333,000 times less massive than the Sun, the shift is imperceptible, just 279 miles or 449 kilometers from the Sun's center. But Jupiter, that 318 Earth mass beast, won't be ignored. The Sun-Jupiter barycenter sits at 1.07 solar radii from the Sun's center. That's outside the solar surface by about 31,000 miles or 50,000 kilometers. When you add Saturn, Uranus, and Neptune to the dance, the solar system's barycenter can reach up to 1.5 solar radii from center, almost 435,000 miles or 700,000 kilometers outside the surface. This means the Sun performs a complex orbital dance around an invisible point that wanders in and out of its body. From outside the solar system, you'd see the Sun oscillate and zigzag through space as if attached to an invisible rubber band. This solar wobble is so pronounced that astronomers use it to discover planets around other stars. If a star wobbles, it's probably being yanked around by invisible massive planets. Space is freezing cold. Minus 459.67 degrees Fahrenheit or minus 273.15 Celsius. The absolute cold of deep space. How many times have you heard it? It's becoming a sci-fi cliche. Astronauts freezing instantly, spacecraft fighting cosmic frost. Too bad it's a half-truth hiding a much stranger and more counterintuitive reality. The fundamental problem is this: space doesn't have temperature in the way we understand it. Temperature measures the average kinetic energy of molecules. how fast they move and bump into each other. But in the near-perfect vacuum of space, there are no molecules. It's like asking what color silence is or how much a thought weighs. A thermometer in the shadow of space would indeed read minus 454 degrees Fahrenheit or minus 270 degrees Celsius, but not because space is cold. The thermometer would simply radiate its heat into space without getting any back. Put that same thermometer in sunlight and it would shoot up to 248 degrees Fahrenheit or 120 degrees Celsius or more. The International Space Station swings between minus 250 degrees Fahrenheit or minus 157 degrees Celsius in shadow and 250 degrees Fahrenheit or 121 degrees Celsius in sun, a variation of nearly 500 degrees. But here's the truly absurd part. The main problem for astronauts isn't cold, but heat. The human body constantly produces heat, about 100 watts at rest, like an old-style light bulb. On Earth, we dissipate this heat through convection. Air cools us. Conduction, we touch cold things. And evaporation, we sweat. In space, only radiation, which is incredibly slow. Spacesuits have elaborate cooling systems with water tubes circulating through the undergarment. Astronauts during EVAs or spacewalks sweat like pigs and must constantly adjust cooling. The ISS itself has enormous radiators to dissipate heat generated by crew and equipment. Paradoxically, keeping things cool in freezing space is one of the most complex engineering problems. It's like being trapped in a perfect thermos where your heat has nowhere to go. Hey Curious Squad, before moving on, answering the question, be sure to subscribe to our channel clicking on the notification bell and leave us a thumbs up so you don't miss out on our daily videos. Diamond is the hardest material in the universe. Diamond, the king of hardness, the undefeated champion of the Mohs scale with a perfect 10. Engagement ring ads proclaiming hard as your eternal love. Spoiler, diamonds aren't eternal either. They burn at 1,562 degrees Fahrenheit or 850 degrees Celsius in air. But the universe laughs at our obsession with crystallized carbon. First off, even on Earth, diamond has lost its crown. In 2009, we created Lon's Delight, hexagonal diamond, which is 58% harder. Cubic boron nitride can be just as hard and survives temperatures where diamond would burn. Lab-created aggregated diamond nanorods are even harder. Diamond, it's just the hardest natural material we commonly find on Earth, which is like being the biggest fish in an aquarium. But let's leave Earth and things get insane. In neutron stars where gravity is so extreme that atoms collapse, there exists something called nuclear pasta. Don't be fooled by the cute name. It's matter so dense that a teaspoon would weigh as much as Mount Everest, and so hard it's 10 billion times stronger than steel. Nuclear pasta forms when protons and neurons get squashed into structures that weirdly resemble various types of pasta. Spaghetti, lasagna, gnocchi. Physicists are clearly hungry when naming things. These structures are held together by the strong nuclear force, not diamond's weak chemical bonds. It's like comparing rope to a titanium chain. And get ready for this cosmic tidbit. On Neptune and Uranus, it literally rains diamonds. The extreme temperatures and pressures in the atmosphere, 1 billion times Earth's pressure, break down methane, separating the carbon which then crystallizes into diamonds. We're not talking specks. Some scientists hypothesize diamonds as big as icebergs slowly sinking towards the core through a liquid methane sea. Imagine diamond storms of millions of carats falling through alien skies, an unimaginable treasure accumulating in an unreachable core. Earth's jewelers would weep. Diamond, our symbol of rarity and hardness. In the universe, it's just well-organized carbon trying to look tough, while neutron stars and gas giants laugh at our naivety. The sun is a small star. And here we have astronomy's most repeated lie. Our modest sun, a common yellow dwarf star of average size, nothing special in the cosmos's vastness. Documentaries say it solemnly. Professors repeat it to teach cosmic humility. Carl Sagan himself said it to make us feel less special. It's the perfect story of stellar modesty. Too bad it's a monumental statistical distortion. Ready for the shock? The sun is bigger more massive and brighter than about 90% of all stars in the Milky Way. Our supposedly mediocre sun is actually in the stellar elite's top 10%. It's like saying a 6'7" NBA player is average height. Technically true if you only look at the NBA. Absurdly false if you consider the entire population. The deception comes from a colossal observational bias. When you look at the night sky, you see Sirius, Vega, Arcturus, Betelgeuse, all monstrous superstars. Even small Sirius is 25 times brighter than the Sun. Rigel, 40,000 times brighter. Deneb, 200,000 times. These are the firmament's celebrities, visible from hundreds of thousands of light years precisely because they're exceptionally bright. It's like judging average human height by only looking at basketball players. The reality? 75% of all stars are red dwarfs, little stars so pathetically dim that even Proxima Centauri, the closest star to us at just 4.2 light years, is completely invisible to the naked eye. These red dwarfs have masses between 7.5% and 50% of the Sun's. If the Sun were a basketball, an average red dwarf would be a tennis ball. Some are barely bigger than Jupiter. And it's not just about size, it's about power. The Sun emits 3.8 times 10 to the power 26 watts of energy. A typical red dwarf, less than 1% of that. TRAPPIST-1, that famous star with 7 planets, it has 0.05% of the Sun's luminosity, 2,000 times dimmer. If the Sun were a stadium floodlight, TRAPPIST-1 would be a candle. But the real humiliation for red dwarfs? Longevity. These little stars can shine for trillions of years. The universe, at its measly 13.8 billion years, isn't old enough for even one red dwarf to have died of natural old age. The Sun will live only 10 billion years total. It's the price of stellar success. The bigger and brighter you are, the faster you burn your fuel. Mercury is a uniform hell. The planet closest to the Sun. Obviously, it's a hellscape where lead would instantly melt everywhere. With the Sun appearing 3 times larger than from Earth, the entire planet must be a ball of scorching rock, right? Surprise! Mercury hosts some of the coldest places in the inner solar system. In permanently shadowed polar craters, temperatures drop to minus 290 degrees Fahrenheit, or minus 173 degrees Celsius. In these eternal darkness pits, billions of tons of water ice sit peacefully just miles from surfaces reaching 800 degrees Fahrenheit or 430 degrees Celsius. How's this possible? No atmosphere. Without atmosphere, there's no way to distribute heat. It's like the difference between putting your hand in a 400 degree Fahrenheit or 200 degrees Celsius oven, bearable for seconds, versus touching a 400 degree Fahrenheit pan, instant burn. Air transfers heat poorly. Direct contact transfers it perfectly. Mercury doesn't even have air. The result is surreal. Imagine standing on a polar crater's rim. Your feet would be on 212 degree Fahrenheit or 100 degrees Celsius rock, but stretch your arm into the crater's shadow and the temperature drops 490 degrees Fahrenheit or 270 degrees Celsius in just yards. Throw water on the sunlit side, instant vapor. Throw it in the crater, eternal ice. Mercury holds the solar system record for temperature swing. From plus 800 degrees Fahrenheit or plus 430 degrees Celsius day to minus 330 degrees Fahrenheit or minus 180 degrees Celsius night. At a single spot. Because Mercury's day lasts 88 Earth days, each area has time to roast to maximum, then cool to near absolute zero. But the craziest part? Those ice deposits have probably been there billions of years, protected by eternal shadow while yards away the sun bakes rock to pizza oven temperatures. It's like having your freezer and oven open side by side forever. The cold of space. We always hear it like a universal constant. Minus 454 degrees Fahrenheit or minus 270 degrees Celsius, near absolute zero. The same everywhere outside the atmosphere. Space is cold, period. But wait, if space is empty, what the hell has a temperature? Vacuum can't be hot or cold. Temperature is a property of matter. And here comes the headache. Actually, when we say space temperature, we mean radiative equilibrium temperature, how hot or cold an object would get there, and it varies enormously depending on location. An astronaut in a spacesuit near Earth, the sun-facing side reaches 250 degrees Fahrenheit or 120 degrees Celsius, and the shaded side drops to minus 250 degrees Fahrenheit or minus 150 degrees Celsius. That's why suits have complex cooling and heating systems. Near Mercury, the sunny side would hit 390 degrees Fahrenheit or 200 degrees Celsius. Near Neptune, even the sunny side would drop to minus 330 degrees Fahrenheit or minus 200 degrees Celsius. Temperature depends on the balance between absorbed radiation from sun, planets, and emitted radiation. Everything above absolute zero emits infrared. In vacuum, there's no conduction or convection, only radiation, a perfect thermos. That's why the James Webb Telescope must stay at minus 380 degrees Fahrenheit or minus 230 degrees Celsius, not because space is cold, but because its huge sun shield blocks sun, earth, moon heat, letting it radiate its heat away until frozen. Remove the shield, and it would warm to room temperature in minutes. Okay guys, is there anything you don't understand about what we've told you? If so, let us know in the comments. And if you want to learn more about the solar system, check out the whole series we've dedicated to it.